Okay, let's dive into what is honestly a mind-bending concept, teaching machines to diagnose their own broken parts through a sort of digital synesthesia. In this explainer, we're unpacking a fascinating piece of research where scientists figured out how to use some of the world's most advanced visual artificial intelligence to flawlessly diagnose audio problems. Now, I know that sounds completely contradictory, right? But the results we're going to look at are going to completely change how you think about machine learning.
We're actually starting with this ancient poetic description of synesthesia from Sinai. The Hebrew Bible recorded this crossing of sensory modalities as a profound event, basically sound rendered visible. Well, thousands of years later, researchers are pursuing a computational analog to this exact idea. They're literally making machines see audio signals.
And this brings us to the key to our magic trick today, cross-modal inversion. Imagine you're trying to fix a broken industrial fan. Usually, you teach an AI to listen to it. But what if, instead, we translate that sound into a picture and then ask a completely different kind of AI to look at that picture? So this poses a multi-million-dollar industrial question. Predictive maintenance, knowing when a machine is going to fail before it actually breaks down, is a massive industry. And the computer vision community has built remarkably effective anomaly detectors. So the question is, can we take this incredibly advanced AI, built entirely for computer vision, and basically trick it into analyzing audio? To really understand why this is such a game changer, we have to look at how things have traditionally been done. Up until now, fixing broken machines with AI required training models on endless hours of domain-specific audio. You had to build custom feature extractors. If you wanted the AI to know what a broken bearing sounded like, you literally had to feed it tons of audio of broken bearings. It's tedious, it's highly specialized, and it's super prone to something called the identical shortcut problem, where the AI actually just reconstructs the anomalies instead of flagging them.
Section 1, the translation trick, or what they call SoundFrames.
Okay, here is where the translation actually happens. The crucial point is how they format this data. A standard digital image is made of red, green, and blue channels, right? Well, the researchers stacked 3 different acoustic metrics into these channels to create an RGB image. The red channel holds the Log-Mel Spectrogram, which captures the raw spectral energy. The green channel holds the temporal delta, capturing transient events. Think of the sharp impulse bursts of a broken gear tooth. And the blue channel captures the instantaneous phase, which tracks the regular periodic rhythm of rotating machinery.
And wow, the visual results of doing this are pretty stunning. When you look at SoundFrames for normal machine operations, they look almost like natural visual textures, kind of like woven fabric or wood grain. But for anomalous audio, say a degraded fan blade, it turns into this vivid, heavily textured RGB image where you can clearly spot elevated energy and disrupted phase structure. It stands out like a sore thumb.
Now for the twist in our magic trick. We take these audio images and feed them into a system called PatchCore. PatchCore is a state-of-the-art vision anomaly detector. But here's the crazy part. PatchCore was trained entirely on ImageNet. That means its entire brain was built by looking at millions of pictures of everyday objects. Dogs, cars, bicycles. It has never seen an industrial spectrogram in its life.
I really want to hammer this point home. 0. This system requires absolutely 0 audio-specific training to diagnose these machines. 0 fine-tuning. The vision model's weights are completely frozen. It only knows what a dog or a car looks like, and yet we are going to ask it to find a broken machine bearing.
Moving on to the results. Flawless execution.
You might be wondering, well, how well can a purely visual AI grade a purely acoustic exam? Looking at the data from the DCASE 2022 benchmark, it scored a perfect 1.000 area under the curve for both fan and bearing machine types. That means perfect detection. It completely outperformed the baseline autoencoders and even beat the top-performing custom-built audio AIs from that year's challenge. And it did all of this without a single second of audio training. There is a massive score separation between the normal and anomalous samples. The margin is just huge. And the ablation study data shows something absolutely fascinating. For these specific fan and bearing machines, just the red channel alone, so the standard Mel spectrogram presented as a basic grayscale image, was enough to hit perfection. Though the researchers do note that for more complex, low-signal faults, like in gearboxes, those green delta and blue phase channels become absolutely critical for picking up transient impulse bursts and speed irregularities.
Next up, visualizing the anomaly. Because you see, this method doesn't just give us a pass-fail grade. It gives us profound visual explainability. And that is incredibly rare in unsupervised audio detection. Since the sound frame is essentially a graph where the horizontal axis is time and the vertical is frequency, we can use a visual tool called GradCam. GradCam is usually used to show where an AI is looking in a photo, like highlighting a dog's face. But here, the vision model's heat map projects directly back onto the audio waveform, literally glowing exactly where and when the machine failed. It isolates the aerodynamic turbulence of a broken fan blade flawlessly.
So the why. Let's unpack the trick. Why does an object recognition AI master audio so flawlessly? How does a model trained on bicycles know what a broken industrial fan looks like? To answer this, researchers measured something called round-trip fidelity. They essentially asked, if we turn the audio into an image and then reverse the math to turn it back into audio, how much data gets lost? And they found that the errors for anomalous sounds are significantly higher than for normal sound.
What they discovered is that broken machine sounds are just mathematically harder to encode. Normal machine sounds produce regular, periodic patterns that look like natural textures, again, like wood grain or fabric, which the ImageNet AI has seen millions of times. But mechanical faults, they create non-linear spectral patterns. When those get translated into our RGB sound frame, they turn into weird, irregular visual textures. The visual AI instantly flags these as bizarre, out-of-distribution patches. From a practical standpoint, this elegant little hack is totally revolutionary for the factory floor. It's lightweight, it's blazing fast, processing over 27 clips per second on a basic free-tier T4 GPU. And since it requires absolutely no domain-specific audio training, it is ready for near real-time predictive maintenance right now. The data distribution shows that the normal scores and the anomaly scores are completely separated by a massive gulf. At the operating threshold, there are 0 false negatives, meaning the system literally never accidentally clears a broken machine. Now, it did catch a tiny 6% false positive rate, but deeper analysis showed those were actually just normal clips with unusual ambient background noise bursts. So we've just seen how researchers tricked a visual brain into mastering sound by simply changing the representation of the data. It's a really powerful reminder that sometimes the absolute best way to solve a hard problem isn't to build a new tool, but to look at the data through a completely different lens. Which leaves us with a thrilling question for the future of artificial intelligence. If we can teach vision AI to master sound with perfect accuracy, what other senses can we teach machines to see? Thanks for joining me on this explainer, and I really hope this sparked some curiosity about the boundless potential of cross-modal AI.